Hello, I present in front of you my work which consists of investigating of natural gas enrichment with high hydrogen participation on combustion characteristics and knock in dual fuel diesel engine. We start the presentation by the introduction, then result and discussion, and we finish by the conclusion. We start by the introduction with growing worries about the safety of the environment and the lack of supplies of crude oil. The great deal of effort has been made to use alternative fuels in engines. For internal combustion engines, natural gas is one of the most attractive available fuels. The dual fuel concept is an effective way for its use. In dual-fuel engines, gaseous fuel is usually injected into the cylinder with the intake air and is compressed in the same manner as in conventional diesel engine. Owing to its high autoignition temperature, the gaseous fuel mixture doesn't autoignite. Near the end of the compression stroke, a small amount of liquid high cetane fuel, commonly referred as the pilot, in this case is the diesel fuel, is injected to ignite the heated gaseous mixture. Natural gas has a slow burning velocity and limited lean burnability. In addition, natural gas with hydrogen is an effective way to mitigate such demerits, since hydrogen is characterized by rapid combustion speed, wider combustion limit, and low ignition energy. For high engine loads operation, the engine risk, risks to go through a hazardous knocking regime. It is usually admitted that knock-in combustion is created from the spontaneous ignition of a portion of unburned end gas in front of the flame front before it is being reached by this one. Depending principally on the temperature and pressure evolution of the end gas, in addition to the rate of the flame development. In this context, the current study explores the effect of natural gas enrichment with high hydrogen concentrations. The percentage of hydrogen concentrations are 20, 30, 40, and 50 by volume in dual fuel mode on combustion characteristics and knock. Combustion characteristics are obtained for four engine loads, that is 20%, 40%, 60%, and 80%. We go to the result and discussion. We start by the combustion characteristics. Incident pressure. The figure shows the variation of incident pressure at low, moderate, and high loads for all examined test blends. The incident pressure peak rises with increasing load, certainly attributed to the increase of the quantity of fuel burned during the premixed combustion process. At low loads, in this case 20% and 40% of full engine load, lower in cylinder pressure is observed for the dual fuel mode relative to conventional diesel, either for pure natural gas or hydrogen gas natural mixtures. This can be explained by the pure gaseous contribution relative to diesel fuel and hence a lower in cylinder temperature. However, the diesel fuel operating mode shows higher pressure peaks than the diesel mode at high loads because of the rise in the amount of primary fuel and higher charge temperature. revealing an enhancement in the combustion efficiency of gaseous fuel. The highest pressure peak value corresponding to the blend composed of 50% of hydrogen. Therefore, at moderate and high loads, adding hydrogen to natural gas resulted in higher pressure peak relative to pure natural gas case. This latter occurs progressively close to the top dead center (TDC). This is explainable by a high diffusion speed of hydrogen that enhances the mixing quality and a higher heat release rate during the rapid premixed combustion period under dual fuel mode relative to the diesel mode as presented in the. We go to the heat release rate. The figure shows the variation of heat release rate with various loads. With regard to the impact of hydrogen addition to natural gas, it can be observed that the heat release rate peak at the premix combustion process decreases relative to baseline natural gas at low loads. The very small amounts of the hydrogen used with natural gas lead to very lean mixtures, negatively impacting combustion efficiency. However, for moderate to high engine loads, the heat release rate peak increases for hydrogen natural gas dual fuel mode in comparison with baseline natural gas mode. This is principally attributed to the improvement in gaseous fuel combustion efficiency due to rapid flame propagation and better ignitability of hydrogen. There are improved mixture quality. The combustion duration. The figure describes the combustion duration for different engine loads with the crank angle. Combustion duration increases as the engine load increases. On the other side, higher combustion duration are observed at a given engine load under the dual fuel mode than that of diesel case, particularly at low and moderate engine loads. However, at high loads that correspond at 80% of full load, the combustion duration becomes higher for conventional diesel compared to the dual fuel operation. Regarding the hydrogen addition to natural gas, the combustion duration is reduced for all cases. This is because the hydrogen's combustion characteristics, with its rapid combustion rate and wider combustion limits, shorten the combustion duration and help to reduce the heat loss across the cylinder walls. Enriching natural gas with high hydrogen concentrations in dual fuel engine in dual fuel mode is an interesting technique for improving engine combustion characteristics up to 80% load without any knock, as shown in the figure. However, beyond this load, at 90% of full engine load, the knocking phenomenon appears and rapidly reaches high intensities, as shown in this figure, and occurs before achieving the maximum output power of the diesel engine. In case of pure natural gas, as shown in this figure, as in the case of pure natural gas, the engine reaches the maximum output power without knocking as observed in the last figure. Occurrence of knock with the hydrogen addition is due to the very low metal number of hydrogen, which implies that hydrogen is extremely vulnerable to produce knock that natural gas to produce knock than natural gas that is mainly composed of methane. Sorry. This can be explained by the relatively low autoignition temperature of hydrogen, 500 degrees Celsius and 580 degrees Celsius for methane. Its high range of flammability of hydrogen. Natural gas has better knock-in resistance due to its relatively lower range of flammability, contrarily to the hydrogen. The hydrogen has also a fast flame velocity. It has also a very short flame kinship distance relative to natural gas that enables flames to move very close to the walls of the cylinder. Knocking combustion causes major engine damage, reduces the efficiency and requires particular attention. Therefore, it is advisable to operate dual-fuel engine with hydrogen enrichment at the safe zone from 20% to 80% engine full load to prevent knock. We conclude the work by conclusions. Natural gas enrichment with high hydrogen participation rates was investigated as a technique for improving dual fuel mode. Impact on combustion characteristics and knock was examined experimentally. The following points summarize the major findings. Natural gas enrichment with hydrogen contributes to enhance the combustion of gaseous fuel. It results in improved heat release rate during the premixed phase of gaseous fuel, which increases the pressure peak, particularly at high loads. Sorry. At high loads, over 18% of engine full load. In our case, natural gas enrichment with hydrogen generates a knock which quickly attains high intensities. Thus, it is advisable to operate dual fuel engine with the hydrogen concentration at the safe zone from 80% to from 20% to 80% engine full loads in our case to prevent knock. Thank you for your attention.